Hi everyone, I'm Zara from Global AI Hub and welcome to our series of webinars. Today's webinar is called Determination of Evaluation Metrics for Object Detection, and today we have with us Alisher Abdulkhaev, who is an ML expert based in Tokyo in Japan. So please let's welcome Alisher. Hi
Hi,
Alisher, how
hey,
are you?
yeah, I'm fine. How are you?
I'm great. So would you like to give us a little background about what you do and what you'll be talking about today?
Yeah, of course, for sure, for sure. And first of all, thank you very much for giving me this chance to give a webinar at Global AI Hub. So yeah, I would like to introduce myself. My name is Alisher, surname is Abdulkhaev. I'm living in Japan right now. I'm working as a computer vision engineer at Browsing. Also, I am co-director at Machine Learning Tokyo. And I'm also doing PhD right now. So this is a very brief introduction about myself. Yeah, I'm very excited to give a webinar today about object detection evaluation metrics. Yeah, if it's okay for you, we can start for presentation.
Yes, so it's a
Cool.
great pleasure to meet you and best of luck for your webinar. Now the stage is yours.
Yeah, thank you. Okay, welcome everyone. And today we are going to talk about evaluation metrics for object detection. And so I would like to thank you for Global AI Hub for inviting us to give a webinar at their platform. And this webinar is kind of collaboration with Global AI Hub and Machine Learning Tokyo. I already did my introduction, but let me do it again. So my name is Alisher. I'm working as computer vision engineer at Browsing. I'm doing my PhD at University of Tsukuba in computer vision lab, and also I'm co-director at Machine Learning Tokyo. You can reach me out through LinkedIn or Twitter. And if you don't mind, I would like to introduce Machine Learning Tokyo for 5 minutes. As I said, I'm one of the co-directors at Machine Learning Tokyo. Machine Learning Tokyo is actually a non-profit organization based in Japan. And last year we won an award of Rakuten Technology Award. And this community is actually founded in 2017 by Susanna and Yuvraj. And we registered as non-profit in last year in May, and representative director Susanna, and 4 of us are co-directors at Machine Learning Tokyo: Susanna, Yuvraj, me, and Dimitris. And right now we have more than 6,000 members and around 50 people as a contributors. You can reach out to our website or our blog and through these links. I'm going to share the slides, and we are going to put this link to the slides in YouTube comments. So actually, Machine Learning Tokyo is dedicated to democratize machine learning through open education, open source, and open science. We actually provide different kind of events, resources, and study groups within MLT. And our goal is to make machine learning accessible to everyone through open science, open education, and open source. And by the way, all events and resources, or like all study groups, are for free. None of them are paid one. After this brief introduction, let me jump into our main topic today. So our topic is evaluation metrics for object detection. Okay, let me explain what's the evaluation metric. And of course, this presentation would be a bit technical one. That means we will be talking more technical stuff rather than the casual one. So feel free to ask any questions at any time, and I will try to answer during the presentation. Okay, what's the evaluation metric? In machine learning or in AI, we usually train a model, and we train a model on given data, and we need to be able to assess these models using some evaluation metrics. This is because we want to know how well is our model performing at given task. And these performance metrics would help us to know whether our model is doing well or not. What I mean, it will help us to assess that if it is underfitting, overfitting, or anything wrong with the data or something else. So that's why I think evaluation metrics are very crucial in machine learning training pipeline. And of course, there's no single magic performance metric. So there's no unique metric for every task. That means there are a lot of different evaluation metrics for different tasks. For example, I think this is the most well-known evaluation metric, which is accuracy. And I'm pretty sure that everyone knows about accuracy. And there's another one, which is recall. And there's another one, which is called precision. And there's another one, which is called mean average precision. And true positives, false positives, true negatives, and false negatives, as well as sensitivity, specificity, and intersection reunion, etc. So this evaluation metrics doesn't include all evaluation metrics in machine learning, of course, but this, just to give an example, these are some examples for evaluation metric. But as we said, there's no single unique performance metric which can work for every task. Okay, before jumping into the object detection evaluation metrics, I need to introduce the basic building blocks. Let me start with them. And the first one is this matrix called true positive, true negative, false positive, and false negatives. True positives means the detections which are correctly identified. And of course, we are going to give more examples in next slides. False positive is incorrectly identified. True negative means correctly rejected, and false negative incorrectly rejected. So sometimes it may be a bit confusing to differentiate between what does true or false means and what does positive and negative means. And actually, this is very straightforward. Once you get this, there wouldn't be any confusion. And true and false, the terms true and false are about ground truth data. And positive and negative are about predictions, our model predictions. And these 4 different metrics are used for different machine learning evaluation metrics. For example, accuracy uses these 4 building blocks: recall and precision, and sensitivity, specificity, and F1 score. All are using these building blocks. All are using this matrix as a building block. Okay, let's start with accuracy. How do we define accuracy using these building blocks? Okay, the accuracy means is that performance metrics in classification problems. So this is special for classification problem, which means the ratio of number of correct predictions to number of all ground truth data or ground truth samples. And here's the formulation for that: true positive added by true negative and divided by the whole data. And let me give 2 or more scenario to get into the accuracy. For example, let's assume you have a data, and in your data you have 7 different samples. That means, or you can call it 7 different data points. And GT means ground truth, which is our data sets labels. And in let's say our first sample is positive, Second one is negative, positive, positive, negative, positive, and negative. So this is our ground truth data. By positive mean, for example, if we want to classify a given object, if a given object is a cat or not, then being a cat is positive example, which correspond to number 1 in this slide. And predictions, which is visualized in blue, is our model's prediction. Okay, we had the ground truth data and we had these predictions. And as you see, our model predicted all zeros, and we would like to calculate the accuracy of our model. So as a human, when we look at the predictions and ground truth, it's obvious that our model is doing something wrong, right? So all predicting 0. And that's why true positive is 0, because our model didn't detect any positive example at all. And as for true negative, so we detected all negatives, and 3 of them was not negative. And false positive is 0, false negative 4, and accuracy is 43. Yeah, as you see, like this may be a bit misleading, and this is the binary classification. And when you see the accuracy 43, that means it's not very good, right? It's like we can call it bad, because chance level is already 50%. Like if you predict randomly, then you will get approximately 50%. But our model is 43. But any people can think this model is performing good, but it's not actually. And in the second scenario, again, ground truth data is the same, and our predictions are all 1, which is not the good indeed. And here's the true positive 4, true negative 0, false positive 3, and false negative 0, and accuracy is 57. As you see, even though both of these predictions are doing nothing at all, and so there's a difference between accuracy and difference between accuracy in the first example and accuracy in the second example. Here's another scenario. I just changed the predictions. In the left one, again, you see our model is doing something like predicting 0 or 1, which may be thought as like good, because like it is doing something, not predicting all zeros or all ones, but so it's detecting most of them incorrectly. So the accuracy here is 28, and in the right side, there's another scenario. In this one, the accuracy is 86. So as you see, so the accuracy metric, although it's the unique metric for classification, although it's the most well-known metric for classification, it's not a unique metric for classification. And so as you see, accuracy may mislead us about our model's performance. And let me give you a visual example. Here you see 2 different images. In the top left, you see one image. In that image, doctor says to woman that she's not pregnant. So it is false negative, because doctor says that it's negative, but it was not correct. So that's why false negative. And in the right bottom, you see doctor says to a man that he is pregnant. So this is another error, and we can call it false positive, because doctor says it is positive case, but it was not the case. So that's why we call it false positive. And just decide which scenario do you think is worse. Is top left is worse or right bottom is worse? Actually, it depends on your expectations, right? So it depends on your expectations. So that means having only this true positive, true negative, false positive, and false negative is still not enough, and to make a conclusion about our model's predictions. That's why we need to define something different, which we call it recall and precision. Recall is actually defining the proportion of actual positives which were predicted as correctly. And precision is what proportion of positive predictions was actually correct. It may be a bit confusing at the beginning, but once you get into this precision and recall, then you will see that this is very useful and this is very important evaluation metric. And let me note two different things. The one is a model that produces no false negatives has a recall of 1, and a model that produces no false positives has a precision of 1. We are going to examples within the same data in the next slide. Again, we have exactly the same scenarios as we had before for accuracy. And here's the formulation for recall and formulation for precision. Recall is defined as ratio of true positives divided by true positive added by false negative. And precision is true positive divided by true positive added by false positive. And in these two scenarios, so we had exactly the same grand truth data, and our model predicted all zeros, and we had exactly the same true positive, true negative, false positive, and false negative as we had before. But in terms of precision and recall, you see the recall is 0, precision is 0, because our model didn't do anything. So that means our true positive was 0. So according to the formulation, both recall and precision should be 0. And in the right scenario, in this scenario on the right, we had again the same grand truth data, but this time our model is predicting all ones. And according to the formulation, we had the recall 1 and precision 0.57. Let's see another examples. So in this example, again, the same grand truth and different predictions, and recall is 0.25, precision is 0.32. And let me explain it a bit more. Why we have recall 0.25? Because we had 4 positive examples in the data, and we could only catch one of them, which is in the beginning, this one. The first one we predicted as positive, and that's why we catch only one of them. And this is a ratio of 1/4. That means 0.25. And as for precision, we detected 3 positive examples, and that means this one, and this one. But only one of them was correct, which is the first example. And that's why this is like 1/3. And that's why we had precision 0.32. And in the example on the right, we have again the same grand truth and different predictions. And we have a recall of 0.75 because we had 4 positive examples, and we could catch only 3 of them. And this is the ratio 3/4, and that's why we have recall 0.75. And as for precision, we have a precision 1 because we detected only 3 positive predictions, and all of them were indeed correct. That's why this model precision is at maximum level, which is 1. And after introducing this, let me jump into the object detection evaluation metrics. If you have any question, please write on the chat so that I can answer and then continue to object detection. If you don't have, let me continue. Yeah, as I said, there's no unique evaluation metric for all tasks. So for every task, we have to define different evaluation metrics, which would help us to assess our model's performance as much as possible. So let me introduce one more evaluation metric, which is intersection over union. Intersection over union is actually measures the localization performance. In object detection, like in classification, we given an image, and we need to classify those images into different classes. But in object detection, we have an image, and there are some objects in the image, and so we need to localize that objects and then classify to particular class. And that means, like, if there are cat and dog in the image, we need to localize the cat and localize the dog and say this is dog and this is cat. So intersection over union is actually a measurement for localization. And if intersection over union metric is above a particular threshold, then we accept that object as correct one in terms of localization. And there another metric in object detection, which is recall and precision, as we have just seen. And there's another two very important evaluation metrics, which are average precision and mean average precision. As you see on the right figure, the intersection over union is explaining what does it define. Red bounding box is the ground truth bounding box, and green one is, let's say, our prediction. And we define the intersection of two bounding boxes, and then divide by the union area of both bounding boxes. And this is the formulation for intersection over union. And in the figure on the bottom, you see three different examples. The one is, in this case, green is the ground truth and red one is a prediction. And intersection over union here is 0.4. And in the middle, which is, we can say it as a good, which is intersection over union is 0.7, and on the most left side, it is almost fitting to the ground truth bounding box, and the intersection over union is 0.9. So as you see, this metric defines how well we fit to the ground truth bounding box. By the way, bounding box means the rectangle which includes the object. So when I talk about bounding box, that means this region which localize the object. And again, let me give a visual example. Okay, we talked about intersection over union, and let's talk about recall and precision. In face detection, and when we talk about recall, it means how many of given faces could we detect. And when we talk about precision, that means how many of detected faces were indeed correct faces. So, for example, in the top left, you see we could localize every single faces in the image, and that's why we have recall 1 and precision 1. Recall 1 because we could detect all faces, precision is 1 because our all detections were correct. And in the left bottom, we had 5 faces, but we could detect only 3 of them. That's why recall is 0.6, which means 3 over 5. Okay, and as for precision, it is still 1 because we detected 3 faces and all of them were correct. And in the right top, you see another example. Even though the recall and precision is exactly the same, because recall and precisions are exactly the same, even though we just switched the faces. Okay, and so it doesn't mean, so recall and precision doesn't consider the individual objects, but considers the overall performance. And in the right bottom, you see different type of predictions in which we had again 3 detections, correct detections, and 1 false detection, which we call it false positive, because our model says it is positive, but it was not. That's why it's called false positive. And in this scenario, our recall value is 0.6 because we detect 3 of them, but there were 5 faces. That's why it is 0.6. As for the precision, we detected 4 faces, Okay, even though one of them was wrong. We detected 4 faces, but only 3 of them were correct. That's why our precision is 0.75. I think face detection is the most, the best example to introduce recall and precision. I hope it's clear for you. We still have 20 minutes. I can slow down. Okay. Average precision is average of the maximum precisions at different recall values with fixed intersection over union. Okay, I know this is too complicated. As we said, like we have to define intersection over union threshold, and let's define it 0.5, which means when we accept that as particular object is localized perfectly. So this metric defines the localization performance. Once we fix the intersection over union threshold, we can have different detections for different models. And here again, like I just wanted to give an example model predictions together with the confidence scores. For example, this phase is detected with 0.9 predictions confidence score, and this is detected with 0.7. This is 0.3 and 0.6 and 0.2, which means our model is not confident enough about this phase, and it's not confident enough about this phase, and this is, in this case, it is too confident about that this is a phase, even though it was not. And in order to evaluate average precision, we have to write different recall values for different thresholds. So don't be confused. We have 2 different thresholds in object detection. One is for intersection over union. One is for confidence score. So these are completely different thresholds. So right now, don't care about intersection over union threshold because we already fixed it to 0.5. And right now we are talking about the threshold about confidence score, which means when do we accept the model's prediction according to model's score. In that case, we have to prepare this kind of table, and we have to list different recall values 0.2, 4, 4, 6, 8, 6 according to the thresholds. For example, in this case, we had a 0.9 phase detected with 0.9 score, which is the most confident one, and we are going to write this here. And next one is 0.7, and at this level we have 2 phases. That's why I'm writing 2. And at 0.6 we have 3, including this one. And at 0.3 we have 4, including this one. And at 0.2 we have 5, all our predictions. And we are asking the question: was it true? Yes. Was it true? Yes. It was not correct. It was not. It was correct, and it was not correct. And we have a recall values, and we have precision values for every particular level. And we need to write all recall and precision values, and just take the average of all these precision values, and this number defines the average precision in our object detection. Okay, so in this particular example, I guess average precision here is 0.81, and also we were talking about mean average precision, right? And so what's the difference between average precision and mean average precision? The difference is when you have a binary object detection or binary classification. That means in our object detection task, we only have faces, right? So we need to localize only faces. So we have only one class, single class, and we have background class, which corresponds to not face class. So that's why you have binary classification or binary object detection task. So in binary case, average precision and mean average precision are exactly the same. But let's say you want to detect cats and dogs. In that case, you will have three classes. The one is cat, one is dog, and the another one is background, which is neither dog nor cat, right? So you would have three classes, and two of them are positive classes, one of them is negative class. And in this scenario, mean average precision is mean of average precision for different classes. For example, let's say we have average precision of 0.8 for cat, and let's say we have average precision of 0.4 for dog, and then our mean average precision would be 0.6, just the average of these two. And I guess since there are two terms regarding the averaging, I guess people decided to use different terms for these two different cases. One, mean is about interclass metric, and average is the among precisions. And for example, there's a very famous dataset for object detection, benchmark dataset, which is called COCO dataset by Microsoft. For COCO contest or for COCO dataset, average precision is the average over multiple intersection over unions. So before we were talking about average precision for different recalls, and in this COCO dataset, they also provide different average precision for different intersection over unions as well. For example, you will see AP at 0.5 to 0.95. That means, so this metric means average precision for intersection over union from 0.5 to 0.95. That means, like, even though we couldn't localize very well, it considers this detection. And even though, and when we localize very well, it's again considered these detections and average through all these different, all four different intersection over union values. And the step size is 0.05, which means they start from 0.5 and 0.505 and 0.6, 0.605. So the step is 0.05 and moving the intersection over union from 0.5 to 0.95 and taking the average of all average precisions. And mean average precision of overall data set is again, once more, the mean of all these average precisions with intersection over unions 0.75, and there are 80 classes in COCO dataset. So calculating the average precision through all classes would be a bit troublesome, but I can say that the mean average precision is one of the stable, one of the best performance metrics. By best, I mean stable, which can assess the model performance very well. When you have two models, if a model A's performance mean average precision is higher than model B, then you can surely decide that the model A is much better than model B. So in face detection, as I said, mean average precision and precision is exactly the same. So because we only had a face class, so again, mean average precision here is 0.81. This is all about my slides, Zara. So we can jump into the question and answering section, if any.
Hi, so you had a great talk. Thanks a lot for your talk. It was really interesting. So actually, I had a few questions to ask you. So firstly, like, what is the future? Like, what do you plan for the future? Like, right now you're working on object detection. Do you plan on, making glasses for like blind people or something out of this?
Sorry, I think I couldn't get your question.
Are you
Uh,
working on like, integrating this computer vision technology into like products, for example, like there's companies out there which are producing glasses for people who can't see and stuff.
okay, got you, got you. Yeah, indeed. In my company, we are working on e-tailer stuff,
Mhm.
and in the e-tailer, we are detecting the fashion items in the image, in the uploaded image, and like localizing hats, localizing sunglasses, t-shirts, or dresses, skirts, something like that. And uh, and after detecting this uh, fashion items, we are searching for similar items in our database and providing these similar products to the user. So I'm actively, of course, using and integrating object detection in my company.
That's actually a really great idea. So we don't have any questions from the people who tuned in, but thanks a lot for your talk. It was really informative and I really enjoyed it. And I hope we can have you here again.
Yeah, should we wait a bit more to people to ask questions, or would you prefer to end right now?
I think right now, like, I can see the live comments. I'm sure you can too. There's no questions. Someone wrote, "I'll write if I have any question." So I guess like generally people ask during the webinars, like if they have any questions.
Okay, there's another question. Do you need to calculate recall values? I guess the question wants to ask about when calculating mean average precision.
Mm-hmm.
Yeah, okay. Um, yeah, indeed. So we can calculate mean average precision like this. Define the threshold, start the threshold from 0 to 1, and just define the step 0.05, let's say. And for each particular threshold, we need to calculate recall and precision for everyone, for every threshold. And we need to like remove the thresholds which has zero recall, and then just take the average from the rest of the examples. So indeed, we need to calculate the recall for every single step. That's correct.
So do you have anything else to add or any final comments you'd like to say about, your work or the future of your company, for example?
Yeah, maybe I would like to talk about machine learning Tokyo, and that's another my question. Uh, oh, there's one more question there. Okay, okay, that was just comment, I guess. Um, is 0.05 step chosen arbitrary? Not arbitrary. This is kind of default step size for this kind of calculations. Um, yeah, is kind of default one. For sure, you can change it, but I guess the final mean average precision wouldn't change by changing the step sizes that much. Even unless you have like thousands of classes, uh, it shouldn't change by the step size. And yeah, I just wanted to talk about machine learning Tokyo. So if you don't mind, of course.
Yeah, yeah, of course,
Uh,
go ahead. I want to know
yeah,
more.
yeah. Yeah, machine learning Tokyo is the community actually, and based in Tokyo. That's why we call it machine learning Tokyo. But right now we are moving to more global. Yeah, more global. So we are holding online study groups.
Mm-hmm.
Right now we have three different study groups ongoing. Four study groups. One about mathematics for machine learning, and three about reinforcement learning, and one is about Facebook, and which is the Fast.ai's book written by Jeremy Howard. And as well as we are having this kind of talks and more technical stuff, webinars or events or like presentations with discussion. And if you would be interested in, please join Machine Learning Tokyo, as well as please join Global AI Hub. I think you guys are doing a great job, and yeah, hope to see some
Thank
collaborations in the future.
Actually, I have to ask you something about Machine Learning Tokyo. So you said you have study groups. So are you focusing on like university students or school students, or you're just like educating people on machine learning? What do you guys do?
Okay, we don't have any kind of restrictions for joining the study groups, but statistically saying, and all people are like, we have wide broad, so we have people from universities, that means university students, we have university professors in study groups, and we have practitioners, and we have core engineers, so we have very different kind of people. And the most important one is we have researchers which are very good at a particular topic. For example, in mathematics for machine learning, we have 2 professors from universities. Like professor means like doing a research at the university, not exact professors, but they're like hosting the events, and we are reading the book during 1.5 hours, and we have a discussion for half an hour, and this repeats every week in weekends. So we don't have any restrictions for joining the study groups.
And are you guys working on some projects or something like in collaboration with each other?
Yeah, we were working at very different projects. Just a moment, I would be happy to show some.
Yeah, can you share something with us?
And let me show you some of our. Yeah, before this COVID situation, we were holding different talks from well-known people. And for example, we once hosted François Cholet, and we hosted Anima from NVIDIA, and also Josh Gordon from Google AI. And we had different MLT projects. And the one, of course, there are more than this projects. But just to say, we had, for example, a project to translate the English resources to Japanese from Stanford Computer Science department. And we had an AGI project in which the guys are developing machine learning models to help people in the farm and to help to decrease the human labor. And we had one of the most interesting and exciting project, which is ML Search. We didn't release it yet, but I think it's going to be online soon, which is a machine learning search, which is the search engine to search for machine learning resources. And
that's for machine learning resources.
Yes, exactly.
Oh, wow.
When you type something on this search, you would get, for example, related papers or related data sets or related resources.
So it's like Google Scholar for machine learning, right?
Kind of, yeah.
That's actually really great.
Yeah. And we had a chatbot in the browser, which runs on the browser, deep learning-based chatbot, and this is already completed. And Kuzushiji optical character recognition is Japanese old-style handwritten images. I think that's called Kuzushiji. I'm not very familiar, but I guess it is this. And the project was targeting to recognize these characters. It's a bit different than like handwritten recognition because there are different kind of figures in Japanese kanjis, and it's more difficult. And we had another project which is MLT 2020, which we were targeting for Olympics in Tokyo, and doing the face detection, age, gender, and emotion detection in front of the crowded places, and guide to the organizers to balance the crowdness. And another one is tactile pattern for visually impaired and blind people, which is blind people should recognize the image. They want to read the image or recognize the image, and since they cannot see, there's a method that is tactile patterns, which you construct an image and in which you can recognize the content by your hand. And we had another one is again chatbot, generative adversarial networks for creative text generation. It was another project, and this paper was actually published at NeurIPS last year.
Oh wow!
And another, one of the most exciting project is CNN architectures. Maybe you guys already seen that. We were holding workshops to explain different CNN architectures, and we have a YouTube channel, we have videos, and we have slides for different CNN architectures. These are brief list of projects we have done, and of course we are doing some more projects at the moment, which we didn't release yet.
Okay, what's this ENGJP project that you have? The Stanford CS project. What's it about?
It is translating the resources from English to Japanese.
Okay, so an online translator, right?
No, it's just these guys are sit down and translated the resources to help Japanese people to get access to Stanford computer science resources.
Okay.
It's just translation.
Okay.
Not any software or something like that.
Okay.
Yeah.
Do you guys hold your webinars and all the courses and everything that you have, your workshops, in Japanese or English?
Everything is in English, even though we are based in Japan. So we want to keep the original contents in original language. And we don't want to lose the content by translating to Japanese, because we guys are not Japanese. So we are holding everything in English.
Okay. I think next time some of us will also join, so we will check your page, and if you have any upcoming webinars, you will see some of us there as well.
Yeah, looking forward.
So anyways, thank you so much for your talk. It was great talking to you and listening to everything you had to say, and I hope you're here again soon, and best of luck for all your projects and for ML Tokyo.
Yeah, thank you very much. I was a bit in a rush to fit the time, but it was much shorter than I expected.
You were actually pretty good. You didn't seem like you were in a rush at all.
Okay.
You were good.
Good.
All right. Thank you so much. Bye-bye. Have a nice day.
Bye-bye. Thank you very much for hosting me. Okay.
Bye-bye.
Thank you. Bye-bye.
So thank you everyone for tuning in. Please tune in next week for our next webinar. Hope you all have a great day. Thank you. Bye-bye.